Welcome to this Getting Started video for CSD Studio Suite. During the next few minutes we would like to show you how to get started quickly and explain some basic features, especially the new ribbon-based graphical user interface. When starting CSD Studio Suite, the application begins with the default view active. You can return to this view at any time by selecting the File ribbon. On the left pane you have direct access to typical file-related options. The New and Recent section contains options for starting projects or quickly loading recent ones. A new project can be created by clicking on the Create Project button in the New and Recent page. This starts the configuration wizard in order to help you to choose the appropriate module as well as the main project settings and result recorders for the particular application. As a demonstration of a simple workflow in CSD Studio Suite, we are going to be modeling a simple monopole antenna. Therefore, we first select microwave and RF, then antennas, and then wire. The configuration wizard shows the recommended solver for this type of application, although other solvers can be selected too, simply by choosing them from the list. Please note that depending on your license, some solvers may not be available. The next page lets you set the units of measurements. These will then be the default when starting the configuration wizard again. Once you have defined the project settings, you can verify your choices in the summary page and change the name of the project template if needed. Finally, press the Finish button to start the appropriate module, which in our case is CSD Microwave Studio. Let's now take a closer look at the new ribbon-based user interface of CSD Studio Suite. The ribbon command bar organizes all the user interface controls in a series of tabs. All of the commands in one ribbon tab comprise a group representing one step in the simulation workflow. The ribbon is designed so that the most frequently used functions are displayed prominently, and each function is shown only during the relevant step of the design process. The following core ribbon tabs are always displayed. The Home ribbon lets you access some of the core settings that you have defined in your configuration. Here you can change the solver, unit settings, or problem type. When opening an existing model, the most frequently used operations are also available here. The Modeling tab displays all commands used to model the structure, such as the import options and tools for creating primitives. In the Simulation ribbon you can set the frequency range, the boundary condition, and the various possible excitations, such as discrete ports and waveguide ports. This is also where field monitors are defined and the solver is started. Once the simulation has been run, the primary results can be processed by using template-based post-processing. This and special functions such as the cylinder scan are collected in the Post-Processing tab. The View ribbon gives access to our view options, such as the view modes, the cutting plane, the working plane, hide and show commands, and so on. The basic mouse modes can always be accessed from the status bar. On the top right corner of the Studio Suite window, you have access to the online help. By pressing the small triangle, you will be able to access, for example, your support account. The following part of the Getting Started deals with the procedure of creating a simple structure. Many complex structures are composed of very simple elements or so-called primitives. In the following, we will draw such a primitive, a brick. First, switch to the Modeling tab and activate the Brick tool. You will be prompted to select the first point of the brick's base in the drawing plane. You may set a starting point by double-clicking a location on the drawing plane. Now you can select the opposite corner of the brick's base on the drawing plane by double-clicking it. Next, define the height of the brick by dragging the mouse. Double-click to fix the height of the brick. Finally, a dialog box will open showing the numerical values of all coordinate locations you have entered. Click OK here to store the settings and create your first primitive. Before we continue drawing other shapes, let us have a look on different methods of setting a point. The simplest way to set a point is to double-click its location in the drawing plane. However, in most cases the structure coordinates have to be entered with high precision. One way to do this is to press the Tab key whenever a location is expected. This brings up a dialog box where you may numerically specify the location. You may specify the position either in Cartesian or in polar coordinates. The latter type is measured from the origin of the coordinate system. The angle is between the x-axis and the location of the point. The radius is the point's distance from the origin. After the first point has been set, the relative option will be available. If you check this item, the entered coordinates are no longer absolute but relative to the last point entered. The coordinate dialog boxes always show the current mouse position in the entry fields. The third way to enter accurate coordinates is by clicking the estimated values using the mouse and then correcting the values in the final dialog box. You may skip the definition of points using the mouse at any time by pressing the escape key. In this case, the shape dialog box will open immediately. Pressing the escape key twice aborts the whole shape generation process. Hitting the backspace key deletes the previously selected point. If no point has been selected, the shape generation will also be aborted. After a shape has been defined, it is automatically cataloged in the navigation tree. You can find all shapes in the Components folder. You may select the shape by clicking on the corresponding item in the navigation tree or by double-clicking on it in the main window. In this case, the corresponding item in the navigation tree will also be selected. Holding down the Control key while selecting a shape allows you to do a multi-select. You may also select ranges of shapes by holding down the Shift key while clicking on the shape's names. Another powerful way to select multiple shapes is the rectangle selection feature. Choose rectangle selection and define a rectangular area in the main view by clicking and dragging with the mouse. You may change the name of a shape by selecting it and choosing Edit, Properties, Rename, or press F2. You can then change the name of the shape by editing the item text in the navigation tree. Now that we have discussed how to select an object, we should spend some time on the grouping of shapes into components. Each component is a subfolder of the Components folder in the navigation tree. Each individual component folder can contain an arbitrary number of shapes. The purpose of the component structure is to group together objects. This hierarchical grouping of shapes allows simplified operations on entire components, such as transformations. You can change the component assignment of a shape by selecting the shape and choosing Change Folder, Change Component. Here you can select an existing component from the list or create a new one by simply typing its name in the Edit field. In the latter case, the newly created components will be automatically named. The component of selected shapes may also be changed by using drag and drop in the navigation tree. The component assignment of a shape has nothing to do with its physical material properties. In addition to its association with a particular component, each shape is assigned a material that also defines the color for the shape's visualization. In other words, the material properties do not belong to the shapes directly, but to the corresponding material. This means that all shapes made of a particular material have the same material properties and are drawn in the same color. The only way to change the material properties or the color of an individual shape is to assign it to another material by selecting the shape and choosing Materials, Edit, Change Material. This option can also be found in the context menu when a shape is selected. Again, this can also be done via drag and drop, as we have seen for the component assignment. When using the New Material option, you have to specify the material name and the material type. Please note that the available material types as well as the corresponding options depend on the currently used module. You can also change the color of the material by clicking the Change button. Use the Material folder field to arrange the materials in different subfolders. After clicking OK, the new material is stored and appears in the Materials folder in the navigation tree. Selecting a particular material in the navigation tree also highlights all shapes that belong to this material. In order to simplify the definition of frequently used materials, a material database is available. A material definition from the database can be added to the current project by selecting Materials, Material Library, Load from Material Library. Alternatively, this can be done in any of the just mentioned places. You may select an existing material from the list and click the Load button to add the material definition to the Materials folder in the navigation tree. Once the material is available in this folder, it can be used in the current project. You can also add a material that has been defined in the current project to the local database by selecting the material in the navigation tree and then choosing Materials, Material Library, Add to Library. So far we have created and viewed shapes by using the default view. You can change the view at any time, even during shape generation. According to the selected mode, the view will change whenever you drag the mouse while holding down the left button. You can select the mode by switching the view modes. The mode setting affects the behavior as follows. Zoom. In this mode, a zoom window can be defined by dragging the mouse. After you release the left mouse button, the zoom factor and the view location will be updated so that the rectangle fills up the screen. Pan. The structure will be translated in the screen plane following the mouse cursor movement. Rotate. The structure will be rotated around the two screen axes. The center of the rotation will be the point on the structure where the mouse button was pressed, indicated by a red mark. If the selected location is outside the structure, the bounding box center point will be used as a rotation center. Dynamic zoom. Moving the mouse upward will decrease the zoom factor, while moving the mouse downward will increase the zoom factor. Rotate in plane. The structure will be rotated in the screen's plane. The dynamic view adjusting mode ends when you release the left mouse button. You can reset the zoom factor by choosing Change View, Reset View, or hit the spacebar. Press Change View, Reset View to Selection, or Shift and the spacebar to zoom to this currently selected shape rather than the entire structure. Since changing the view is a frequently used operation that will sometimes be necessary even during the process of interactive shape creation, some useful shortcut keys exist. If you drag the mouse while pressing the corresponding key and the left button, changes the mode as follows. Control instantly changes to the rotate mode. Shift changes to the plane rotation mode, and Shift and Control gives the pan mode. A mouse wheel movement has the same effect as the dynamic zoom. By default, the origin for this operation is located at the current mouse pointer location. Optionally, pressing the Control key while using the mouse wheel performs a zoom operation around the center of the screen. In addition to these options, some specific settings are available to change the visualization of the model. You may toggle the visibility of the coordinate axis and the working plane. This setting chooses whether all shapes are displayed as simple wire models or as solid objects. So far you have seen how to model simple shapes and how to change the view of a model. This section focuses on applying geometric transformations to the structure. First, select the shapes you wish to transform. This can be done either by double-clicking or selecting the object from the tree. You can then open the Transformation dialog box by choosing Tools, Transform, or by choosing the item Transform from the context menu. In the dialog box, you are asked to select one of the following transformations. Translate. This transformation applies a vector translation to the selected shape. Scale. By choosing this transformation, you can scale the shape along the coordinate axis. You may specify different scaling factors for each coordinate direction. Rotate. This transformation applies a rotation of the shape around the coordinate axis by a fixed angle. You may additionally specify the rotation center in the origin field. The center may be the center of the shape or any specified point. Specify the rotation angle and axis by entering the corresponding angle in the entry field for the corresponding axis. Mirror. This transformation allows one to mirror the shape at a specified plane. A point in the mirror plane is specified in the origin field, and the plane's normal vector is given in the mirror plane normal input field. For all transformations above, you may specify whether the original shape should be kept or deleted by toggling the copy option. Furthermore, you can specify in the repetition factor field how many times the same transformation will be applied to the shape. This will produce new shapes when the copy option is active. Once a particular type of transformation is selected, corresponding handles will be shown. The actual transformation parameters can either be specified by entering numerical values in the input fields or by dragging the handles with the mouse. Let us apply a rotation to the shape by setting a rotation angle, and to produce multiple copies as the transformation is applied twice. In case the copy option is not used, the name of the transformed shape is kept. If the copy option is used, the shape name is extended by 1, 2, 3, etc. This is done in order to obtain unique names for the shapes. Probably the most powerful operation to create complex shapes is to combine simple shapes using Boolean operations. These operations allow you to add shapes together, to subtract one or more shapes from another, to insert shapes into each other, and to intersect two or more shapes. You can access the following Boolean operations by choosing the corresponding items: Boolean, add, subtract, intersect, or insert. These operations are accessible only when a shape has been selected. In the following, this one will be the first shape. After the Boolean operation has been activated, you will be prompted to select the second shape. Pressing the return key performs the Boolean operation. The result depends on the type of Boolean operation. Let us now step through the different Boolean operations. As an example, we look at a brick and a sphere. Activate the Boolean operations and observe the results. Add brick to sphere. Add both shapes together to obtain a single shape. The resulting shape will assume the component and material settings of the first shape. Subtract sphere from brick. Subtract the first shape from the second to obtain a single shape. The resulting shape will assume the component and material settings of the shape from which the first shape is subtracted. Intersect brick and sphere. Intersect two shapes to form a single shape. The resulting shape will assume the component and material settings from the first shape of this operation. Trim sphere, which is insert brick into sphere. The first shape will be trimmed by the boundary of the second shape. Both shapes will be kept. The resulting shapes will have no intersecting volume. Insert sphere into brick, or trim brick. The second shape will be inserted into the first one. Again, both shapes will be kept. The resulting shapes will have no intersecting volume. Note that not all of the Boolean operations above are directly accessible. When multiple shapes are selected, you can access the Boolean add operation to unite all selected shapes. You can also select more than one shape when you are prompted to specify the second shape or Boolean subtract, intersect, or insert operations. Many construction steps require the selection of points, edges, or faces from the model. This procedure, the so-called picking, is highly versatile for obtaining coordinates or geometrical information. For each of the pick operations, you must first select the appropriate pick tool. After you activate a pick tool, the mouse cursor will change, indicating that a pick operation is in progress. In addition, all pickable elements will be highlighted in the model. Now you can select the desired item by double-clicking it. As soon as you double-click the desired element, the pick mode will be terminated and the selected item will be highlighted. Note that if the Keep Pick Mode option is activated, the pick operation will not terminate after double-clicking. In this case, you have to cancel the pick mode by pressing the Escape key. The following list gives an overview of the available pick modes. Whenever the main structure view is active, keyboard shortcuts can be used to activate a particular pick mode. The main structure view can be activated by left-clicking once on the main drawing window. Pick point, edge, or face. Double-click close to an edge, an endpoint of an edge, or a face. The corresponding item will be selected. Pick edge endpoints. Double-click close to the endpoint of an edge. The corresponding point will be selected. Pick Edge Center. Double-click on an edge. The midpoint of this edge will be selected. Pick Circle Centers. Double-click on a circular edge. The center point of this edge will be selected. Pick points on circles. Double-click on a circular edge. Afterward, an arbitrary point on the circle will be selected. This operation is useful when matching radii in the interactive shape creation modes. Pick Face Centers. Double-click on a planar face of the model. The center point of this face will be selected. Pick Point on Face. Double-click on a point on the model to select it. Pick Edges. Double-click on an edge of the model to select it. Pick Faces. Double-click on a face of the model to select it. Pick Edge Chain. Double-click on an edge of the model. If the selected edge is a free edge, a connected chain of free edges will be selected. If the selected edge is connected to two faces, a dialog box will appear in which you can specify which one of the two possible edge chains bounding the faces will be selected. In both cases, the selection chain stops at previously picked points, if any. Pick Face Chain. Double-click on a face of the model. This function will automatically select all faces connected to the selected face. The selection stops at previously picked edges, if any. The pick operations for selecting points from the model are also valid in the interactive shape creation modes. Here, whenever you are requested to double-click in order to enter the next point, you may alternatively enter the pick mode. After leaving this mode, the picked point will be taken as the next point for the shape creation. Previously picked points, edges or faces can be cleared by Clear Picks or D. One of the most common applications for picked edges is the chamfer and blend edge operation. We assume you have created a brick and selected some of its edges. Now you can perform a chamfer edge operation, which can be activated by choosing Blend Chamfer Edges. In the following dialog box, you can specify the width of the chamfer. Alternatively, you can perform a Blend Edges operation by choosing Blend Edges. In the following dialog box, you can specify the radius of the blend. The chamfer and blend tools are common operations on picked edges. Extrude, rotate and loft operations are equally typical construction tools for use on picked faces. In the following, we assume an existing cylinder with a picked top face. Now we can extrude this face by simply setting Shapes, Extrusions, Extrude. When a planar or cylindrical face is picked before this tool is activated, the extrusion refers to the picked face. If no face is picked in advance, an interactive mode will be entered in which you can define polygon points for the extrusion profile. The extrusion tool has created a second shape by the extrusion of the picked face. For the rotation, you should start with the same basic geometry as before. The rotation tool requires the input of both a rotation axis and a picked face. The rotation axis can be a linear edge picked from the model or a numerically specified edge. In this example, you should specify the edge by selecting the Pick Edge from Coordinates. Afterward, you will be requested to pick 2 points on the drawing plane to define the edge. In the Numerical Edge dialog box, click the OK button to store the edge. Afterward, you can activate the Rotate Face tool by selecting Shapes, Extrusions, Rotate. The previously selected rotation axis is automatically projected into the faces plane. In this dialog box, you can specify an angle and click OK. Note that the Rotate tool enters an interactive polygon definition mode similar to the one in the Extrude tool if no face is picked before the tool is activated. One of the more advanced operations is generating lofts between picked faces. Assume we have constructed the following model by defining a cylinder and a brick in some distance. Now pick the adjacent top and bottom faces of the two primitives. Afterward, you can activate the Loft tool by selecting Shapes, extrusions, loft. In the following dialog box, you can set the smoothness to a reasonable value and click the preview button to get an impression of the shape. Drag the smoothness slider such that the shape has a relatively smooth transition between the two peaked faces before clicking OK. Finally, add all shapes together by selecting all three and using the Modeling, Tools, Boolean, Add operation. Now you can pick the two planar top and bottom faces of the shape. Select the shape by double-clicking on it and initiate the Shape Tools, Shell Solids or Thicken Sheet tool. Note that the Shell command will be accessible only when a shape has been selected previously. In the dialog box, you can specify a thickness and click the OK button. Picking the two faces before entering the shell operation has the effect that the selected faces will later be openings in the shell structure. If no faces are selected, the structure will be shelled to form a hollow solid. The ability to create local coordinate systems adds a great deal of flexibility to the modeler. The aim of a local coordinate system is to allow the easy definition of shapes even when they are not aligned in the global coordinate system. The local coordinate system consists of three coordinate axes. In contrast to the global x, y and z axes, these axes are called u, v and w. The local coordinate system is also known as the working coordinate system. Either the local or the global coordinate system can be active at any time. Any geometry data entered are stored in the currently active coordinate system. You may activate or deactivate the local coordinate system with WCS, local WCS, or from the WCS context menu item. The most important operations on the local coordinate system are accessible directly in the Modeling tab. Toggle WCS on or off, transform WCS, align or fix WCS. The most common way to define the orientation of a local coordinate system is by selecting Align WCS or W. Hovering over the highlighted points, edges or faces shows a preview of the new WCS. This WCS can be activated by double-clicking on the highlighted item. Another option is to pick points, edges or faces of the model in advance and align the WCS with these items by selecting WCS, Align WCS. When a point is selected, the origin of the local coordinate system is moved to this point. When 3 points are selected, the UV plane of the WCS can be aligned with the plane defined by these points. Additionally, this function will move the origin of the WCS onto the first selected point. When an edge is selected, the U-axis of the WCS may be oriented such that it becomes parallel to the selected edge. Finally, a planar face can be selected, with which the UV plane of the WCS can be aligned. Together with the available shortcut keys for the pick mode, this is the most efficient way of changing the location and orientation of the WCS. Besides aligning the WCS with items selected from the model, there are 2 more ways of defining the local coordinate system. Define local coordinate system parameters directly. In this dialog box you may enter the origin and the orientation of the W-axis and the U-axis directly. Transform local coordinate system. In this dialog box you can translate the origin of the local coordinate system by a specified translation vector. You can also rotate the local coordinate system around one of its axes by a specified rotation angle. The second option is especially powerful when combined with the big alignment options described above. The history tree is a powerful tool to edit an already existing object. Assume that you want to change the radius of the cylinder in the previous example. You can select the corresponding shape by double-clicking it and then choosing Properties from the Modeling ribbon or from the context menu. You can now simply click the Define Cylinder item. As soon as you have selected an editable operation from the history tree, the corresponding structure element will be highlighted in the main view. Please note that subsequent transformations will not be considered by this highlighting functionality. After clicking the Edit button in the History Tree dialog box, the Cylinder Creation dialog box will open. You can now alter the cylinder radius and click the Preview button. You will get an impression of how the structural changes will influence your model. If you are happy with the result, click the OK button to update the structure. Note that subsequent transformations will not be visualized by the Preview option in the Shape dialog box, but will be applied when you update the model. Another complex shape generation option is based on curves. A curve is a 3D line drawn on the drawing plane. After a curve has been defined, it can be used for more advanced modeling operations. The following explanations give you only a basic introduction to the way curve modeling works. Please refer to the online documentation for more information. Let's start with a blank project. Use Curves Rectangle to create a new curve item and draw a rectangle on the working plane. Creating curve items is similar to constructing solid primitives. Next, draw a circle on the drawing plane which overlaps with the rectangle. Activate the circle creation by choosing Modeling, Curve, Circle. As a result of the previous steps, you now have two curve items, Rectangle 1 and Circle 1. Now trim both curve items so that the resulting curve contains only the outlines of both curve items. First select one of the curve items, here Rectangle 1. Afterward, activate the Trim Curves operation by choosing Curve Tools, Trim Curves. You will be prompted to select the item to be trimmed with the rectangle. Select the circle and confirm your selection by pressing the return key. The next step will prompt you to double-click on any curve segments you wish to delete from the model. When you move the mouse across the screen, all selectable curve segments at the mouse location will be highlighted. You should now delete two segments so that the result looks like this. Now you can activate the local coordinate system and rotate it around its U-axis. The next action is to draw an open polygon consisting of 3 points on the drawing plane by using Curves, Polygon. Based on these two disjoint curves, you can create a solid using the Sweep Curves operation. This can be initiated by choosing Curve Tools, Sweep Curve. As soon as this operation is activated, you will be prompted to select the profile curve. Double-click on the curve consisting of the rectangle and the circle. After the profile is selected, you will be requested to double-click on the path curve given by the polygons curve here. This short introduction into curve modeling provides a very basic understanding of these powerful structured drawing tools. This section focuses on a rather tedious part of model creation, the definition of conducting traces. Some structures require many traces, which often entail many time-consuming construction steps. The Trace tool simplifies the creation of solid traces with finite width and thickness based on the definition of curves. To practice using this powerful tool, draw an open but continuous curve. I will use a spline. Based on this curve, you can now easily create a trace by choosing Curve Tools, Trace from Curve. As soon as this operation is activated, you will be prompted to select the trace's curve. After selecting the curve, you can specify the metallization thickness and width of the trace. You can also specify whether the trace should have rounded caps at the start or end of the trace's path. The resulting trace might look like this, with rounded caps at the end of the trace only. Since bond wires are frequently used structure elements, a dedicated bond wire tool is available. The easiest way to define a bond wire between 2 points is to first pick those points. Once the points are picked, you can open the bond wire dialog box by choosing Shapes, Bond Wire. You can also open the dialog box without having picked any points. In this case, you may specify the coordinates of the bond wire start and end points numerically. The type of the bond wire can be spline, JEDEC 4 or JEDEC 5. The location of the spline's maximum can be specified, whereas the other two models accept standardized parameters. Those are described in the online documentation. You may also assign a finite radius to the wire by specifying a non-zero entry in the radius field. The wire will still be modeled infinitely thin, but the solver module will apply a special model to the wire in order to take the finite radius into account. Please note that this feature is not supported by solvers based on tetrahedral grids. In addition to this option of modeling the bond wire as infinitely thin wire, the dialog box also supports the creation of solid bond wires. This can be activated by ticking the solid wire model option. As for every other solid, a solid bond wire needs a material to be assigned to it. The termination of the bond wire may be set to any one of the following types. Natural, the wire will be a solid tube with perpendicular cuts at the end. Rounded, the wire will be terminated by a part of a sphere. Extended, this is the most powerful option. In this case, the wire extends toward the plane where it ends. So far we have focused on how to change a structure that has been entirely constructed within the built-in modeler. However, sometimes the model will consist of an imported geometry for which no information about the modeling process is available. This section will illustrate that even in these cases the structure can be parameterized using local modifications. To practice how to use these advanced modeling tools, go ahead and create a model similar to this one. In this structure, you should first use the Pick Face tools in order to select the chamfer's face. Then you can initiate the Remove Feature command by selecting Modify Locally, Remove Feature. As you can see, the gap that would be produced by simply removing the face will automatically be closed by the Remove Feature operation. Afterward, pick the cylindrical face and select the Modify Locally command. A dialog box will open where you can modify the offset of the cylindrical face. This can be done either by dragging the yellow arrow or by modifying the offset edit field in the dialog box. Press Apply to confirm the change. Now you can select the top face and also modify the height of the cylinder by dragging the yellow arrow again. After pressing the Apply button, the model finally looks like this. The local modifications are powerful modeling operations. However, the modifications will fail if there is no unique solution for closing the gaps. You should play around a bit with these tools to get an impression of what is possible.